video. So in the last video we have discussed about the interference, the retardation, the constructive and destructive interference. So today we will start with polychromatic and monochromatic light. So a monochromatic light consists of light wave that are essentially of one wavelength, like the red light. The red light consists of wavelengths which falls in the red region. In polychromatic light, this is not the case. In polychromatic light, there are waves of different wavelength. Like the white light we see is not a single wavelength. It is composed of all the wavelengths in the visible spectrum, or it can be or white light can be produced by mixing two complementary colors. Like here we see in the chromaticity diagram, there are three primary colors like the green, red and blue. If we mix green with red, we get the yellow. So like this, if we mix two colors, we can get a new color. So the new color, we perceive that as a monochromatic light, but it is not a monochromatic light in actual. It is composed of two different colored wavelength. So here it is a table that gives us the different colors and the corresponding wavelength. The violet has a wavelength range from 380 to 450 nanometers, and as we go down the wavelength increases. So red light have the highest wavelength ranging from 620 to 750 nanometers. So next we will talk about the light matter interaction. What happens when light interacts with matter? So the first property of light that we will discuss is velocity. So as we know, the velocity of light in vacuum is 3 into 10 to the power 8 meter per second, which is the highest velocity of light possible. But when it interacts with any medium or any material, its electric vector interacts with the electronic environment of the medium, and each interaction it takes a finite time, so its velocity changes. And the second property is reflection. When light falls on a smooth surface, it gets reflected, and as we know in the law of reflection, that incident angle is always equal to the refracted angle, I equals to r. In refraction, when light falls in the interface between two mediums, it enters the second medium and it doesn't follow the path it was following earlier. It bends slightly. Whether it bends towards the normal or it bends away from the normal, it depends on the relative refractive index of the mediums. So what is the refractive index? So refractive index is the ratio of velocity of light in vacuum and in the medium. So as we know, velocity of light in vacuum is highest, so Ri will always be greater than 1. Most of the materials have Ri ranging between 1.4 to 2.0. So how much the light is bent when it travels from one medium to the other? To describe this, Snell's law is very useful. Like here, sin theta 1 by sin theta 2 is equal to n2 by n1. Here theta 1 is the incident angle and theta 2 is the refracted angle. N1 is the Ri of this medium and N2 is the Ri of this medium. So there is other phenomenon that arises in refraction is total internal reflection. Total internal reflection takes place when the light travels from a denser medium to rarer medium. When light travels from rarer to denser medium, always some amount of energy is transmitted through or reflected through the denser medium. But in opposite case, it is not always the true. Like when light travels from a denser medium to rarer medium, it is refracted away from the normal. So after a certain angle or at a certain angle, when the light falls on the interface between the two medium, it is refracted at an angle of 90 degree. That means the light follows the interface between the two mediums. So if the light falls at an angle greater than this angle, which is called critical angle, the light will be reflected at an angle greater than 90 degree, which means the light will be reflected back into the former medium. So this critical angle can be calculated using the Snell's law. Here n2 by n1 is equal to sin theta 1 by theta 2. Here theta 1 is the incident angle and theta 2 is 90 degree, as we know, for critical angle or total internal reflection. So next properties that come are dispersion and absorption. So that this bending of light or this refraction of light changes with the wavelength. Red has the highest wavelength and it is refracted less than the violet, having the having the shortest wavelength. So the short wavelength having lights are refracted more than the large wavelength having lights. Like in this case, the wavelength is when the wavelength is 700 nanometer, index of refraction is very low, and as we go towards the shorter wavelength, the index of refraction increases. So this is called normal dispersion. There in some case we may see some anomalies which are called abnormal dispersion. This arises due to strong absorption of a material at certain wavelengths. These wavelengths may or may not be in the visible spectrum of light, and the color of a material arises due to this absorption phenomenon. The color of light it absorbs and the color of light it transmits determines which color the material. So here comes polarization, which is the single most important property of light in optical mineralogy. So the light that comes from sun or that comes from incandescent bulb is not polarized. By that I mean the electric vector of these lights are not confined to a single plane. They vibrate in all the directions. So a polarization of light can be of three types. It can be plane polarized. In plane polarized light, the electric vector vibrates in a single plane. This is a plane polarized light. In circularly polarized light, there are two plane polarized light that vibrates at right angle to each other. They have the same amplitude and they have retardation of 1 by 4 lambda. And in case of elliptically polarized light, we have retardation other than 1 by 4 lambda. So there are different methods of polarization of light. So first one is selective absorption. In case of selective absorption, we use thick and anisotropic materials like tourmaline. So what happens is this: when an unpolarized light enters these crystals, it splits into two rays, and one of the rays is absorbed, and the ray that comes out from the crystal is plane polarized. Like in this case, the unpolarized light is splitted into this ray and this ray, and among them this ray is absorbed and the ray that comes out have a single plane of vibration. So another method is double refraction, and this is the most widely used method for optical mineralogy. And double refraction is a property of anisotropic materials. When light enters an anisotropic material, it splits into two rays, and we use the principle of nickel prism to polarize light using double refraction. So a nickel prism is a clear calcite crystal which is cut along its diagonal and glued back using balsam. So balsam has a refractive index of 1.537. So when an unpolarized light enters the nickel prism, it splits into two rays, the ordinary ray and the extraordinary ray. So this is extraordinary ray is expressed as omega, and the extraordinary ray is expressed as epsilon. So omega has a Ri greater than 1.537, whereas epsilon has an Ri less than 1.537. So when these two rays hit the balsam surface, the ordinary ray gets totally internally reflected and it gets absorbed by the black coating, but the extraordinary ray passes through the crystal and comes out as a plane polarized light. Next comes the reflection. So light can be polarized by the principle of reflection also. So when an unpolarized light hits a smooth surface, the reflected light is partially polarized. To get complete polarization, the incident ray must hit the surface at a certain angle where the reflected ray and the refracted ray are at right angles. So this angle is called Brewster's angle, and we can derive an equation for Brewster's law using the Snell's law. Like n2 by n1 is equal to sine theta 1 by sine theta 2. So we know that this angle is 90 degree. So if this is theta 1, this is theta 2, so theta 2 will be equal to theta 90 minus theta 1. So sine theta 1 minus sine theta 2 will become sine theta by cos theta, which is equal to tan theta. So this property of polarization due to reflection is used in preparing sunglasses. Like when sun rays bounces back from the surfaces like lakes or pavements, it is horizontally polarized, and our sunglasses are or only allows the vertically polarized light to pass through, so it greatly reduces the intensity of the light that is coming, that the reflected light coming out of the surface. We can light can be polarized by the principle of scattering also, which is not very important for optical mineralogy. So but we have to keep some things in mind, like scattering is responsible for blue color of the sky. So this brings us to the end of our discussion on the nature of light. In the next video we'll discuss about optical microscope. Thanks for watching, and please subscribe to the channel The Earth Post.